Well, good morning. It's 9:32 on Wednesday, the 11th of October, 2016. It's supposed to be my Cal 2 class, Math 126, and right now I'm the only one in the room, so hopefully the others will be coming in. It has been pretty rough weather for part of the morning, so maybe that delayed people, but anyway, we're going to continue. I've got two announcements I want to make on Screencast-O-Matic, trying to make sure everybody gets to hear it. The first of these, by the time it uploads, you're not going to have a lot of time to do, but let me tell you again, today, Wednesday, the 30th of November, is the last day to withdraw from a class this term. That's a full-term class or second mini-term class. Last day to withdraw. Withdrawals do not hurt you academically beyond putting back your graduation or something like that. They could have some financial aid implications if you have either withdrawn or made a D or an F before the same class, and then you withdraw again. Financial aid will not pay for it a third time. It will pay for it the second time, but not the third. So if that's the case, but the only time I would be withdrawing from a class anyway would be when I had absolutely no chance of passing, making better than a D or an F. And if you are going to make a D or an F, you're going to have to take it over anyway, so you're going to have to push back. That may delay your completion, same as withdrawing would, but with a D or an F, it hurts your grade point average. Okay, financial aid, if you're going to make a D or an F, you're going to have to take it again. If they weren't going to pay for it with withdrawal, they're not going to pay for it for this. So all it does is keep your grade point average from getting worse. Now, one of the students in my last class told me something that I had not heard before, that someone in financial aid told her, something about if you're failing other classes, if you withdraw from a class, you're going to have to pay for it. I have never heard that before, so you might want to check with financial aid office before you make a withdrawal. So I would suggest that. All right, with that said, that was the first of the announcements. The second of these is, and this one you have a little more time on, but they have now opened student course evaluations for fall term. So if you you're in the course, obviously, please do the student course evaluation for every class that you're in. Now, they probably will ask for one or two other evaluations, things like library or registration process or something like that, building upkeep, maintenance, something. You may get other areas you have a survey on. Please do all the surveys they request. I really like to see the student course evaluations for the course, but also the folks in the libraries and food service or bookstore or whatever, they count on those, you responding to their surveys. I get to talk with you every other day, but they don't. So please do all the surveys that are out there. All right, that said, let's move on to, I wish someone was here. I'd ask if there are any questions, but there aren't. So let's pick up where we left off last time. This is the area of a surface of revolution. Okay? I'll blow this up some to make it a little easier to see. I assume it does this on Screencast-O-Matic too, because whatever's projected here is supposed to be what's recorded. The area of a surface of revolution, let's assume that you have some function that is greater than or equal to 0. Okay? They do that so when you revolve around the x-axis, you don't have it crossing itself. Okay? So assume that this f of x is always non-negative, positive, greater than or equal to 0. And that f prime does exist and is continuous on the interval of interest a to b. So your f prime has to exist and be continuous on that interval a to b. Then the surface area S of the surface obtained by rotating the graph of f of x about the x-axis from a to b, x going from a to b, is then this. And it should ring a bell with stuff we've done before. And what I'm going to do here, and I know it's going to shrink this back, but let me get my pen done again. remember, here's our picture of what's going on here, okay? Here is your curve from A to B, okay? Now you're going to revolve this around the x-axis, okay? Now, let's look at this curve here. The first derivative exists everywhere. It is continuous everywhere, okay? It wouldn't be if it had some things like that. Those are called cusps or angles or other things like sharp deviations. But as long as it's a nice smooth curve, the first derivative exists and is continuous on A to B, okay? These would be examples of things that wouldn't be smooth and continuous, okay? The surface area of the surface obtained by rotating that f of x around, this is f of x by the way, around the x-axis would then be to take this and do it around like this, and this would be rotated around, okay? Now, picture, say, this little segment right here, okay? This little segment of your f of x, okay? Well, the length of that segment was, basically, you go back, that's your arc length. That's on Theorem 1, formula for the arc length, was the integral from A to B. We're just going to do a little piece of this. The square root of 1 plus f prime squared dx. So basically, this part right here is the length of that segment, the dx part, okay? When you integrate from A to B, that would give the whole thing, okay? Now, your f of x was the height of that, okay? And the 2 pi, that's your radius that you're going around. The f of x is your radius, and you're revolving that around, so you've got this this slice here. The surface area is that little arc length rotated about a radius of f of x, your y, okay? 2 pi times that radius times the arc length. That gives you, and you integrate that from A to B, that gives you your entire surface of revolution, okay? Let's do example 4. I think there's a picture for that one. It looks a little different on here than it does in your book. What they do is show the finished product. This shows your initial, what you're going with, okay? But example 4 is calculate the surface area of the sphere of radius capital R. Well, what they show here in this figure, your figure in your text, if you got the new edition, shows that sphere. And then they show this function as being what you're rotating. This showing what you're rotating, and ultimately that will produce the sphere, okay? Because when you rotate this, and of course if I go to draw on it, it's going to shrink back. So if you rotate this about the x-axis, you get this little segment here rotated around there. And you integrate from minus r to r, you could, but well, I'll talk about it. So anyway, let's do this. The graph of f of x equal, and now it's shrunk, it's hard to see, but this is your f of x. It's the square root of r squared minus x squared. Because when x is equal to 0, of course, you would be, when x is equal to 0, you would be up here, your f of x would be r, okay? When x is equal to r, that would be 0, or minus r, that would be 0. All right. What's that? Yeah.
I take a long way back. I need to the freeway.
Uh-huh.
My car is not good.
Oh, I
It's
see.
an old car.
Uh-huh.
I don't want to drive fast.
Right. Especially in weather like this.
Yeah.
Okay. So it's here. Hopefully one or both of the other two guys will be showing up. I already started on the class, and while we're waiting for the projector to come on, I'll repeat it in case you don't go back and listen to it. I'll put it on the Screencast-O-Matic at the very beginning. The two major announcements, and not that you need to know either one of them, but I want in case you know someone who might need this. Today, Wednesday the 30th of November, is the last day that you can withdraw from a class. Okay, so if you know of anyone, someone you're tutoring or helping or something, classmate or something that's way behind, no chance of pulling out anything better than a D or an F out of course, way better to withdraw than to risk that. Okay?
Is Theo still on the register, like Theo, the other guy?
Yeah, he, as far as I know, he's still in the class. Last time I checked, he still was. I don't know what's happened to him. So I know he had a very severe illness in his family, and he was having to do a lot of helping, taking either his mother or grandmother and somebody, but whoever it was, he was having to take care of her and take her to the doctor and all sorts of things. So I'm hoping, that's why I keep saying it, putting it on Screencast-O-Matic, if he can't pull it out, he needs to withdraw, and but all I can do is this. I don't.
He's a very bright student.
Yeah, he sure seemed like it. So that's the first. The second one is they have open student course evaluations. So please do those and do all the evaluations they ask for. You know how to access it and everything else, right? Okay. All right. So this was example 4 on page, well, I don't know what page it is in your book. It's in my text. It's in section 8.1. My text is the new edition. It's around page 477. All right, and here's Marcus. All right. I'll repeat this, not that you necessarily would need to know it, but the two major announcements are today is the last day to withdraw from the class. Now, I'm not suggesting you need to, you don't, but I need you to know that. So if you know of someone who is in really bad shape in a class, let them know today's the last day to withdraw. And withdrawing does not hurt you academically at all. It has financial aid implications, so you need to know that. But if someone is hopelessly behind in a class, no way they're going to get better than a D or an F in the class. It's better to withdraw than it is to fail and make a D. Because if you fail and make a D, you're going to have to retake the class anyway. Withdrawing, you'll have to retake the class anyway. Failing or making a D hurts your grade point average. Withdrawing does not. So even if it hurts your financial aid, it's going to hurt it if you fail or you make a D too. So I see no reason not to withdraw. But now a student in my last class said someone in financial aid office told her something I've never heard before, that if she's failing more than one class, if she withdraws, she has to pay the money back or something like that. I've never heard that. So we'll try to find out about it. I haven't had a chance to ask about it. All right. We're doing example 4 for your new text. It's on page 447, section 8.1. Now, the figure doesn't look the same. This is the figure from her text, the older edition. It looks like this, except you see the whole sphere, not just the curve, okay? The curve is listed there, okay? Now, what we need to do with this is first thing I would do with it is rewrite this as r squared minus x squared to the 1/2 power. I would definitely do that because the next thing you're going to do is take a square root. Take a derivative, Take a derivative. And what is a derivative? What is f prime of x then? Say again? It's what? Chain rule, yeah. Say again? Page 447. Top of the page. Okay. What's your F prime? Okay, it's got an X in it. It's actually a minus 2X from the chain rule times R squared minus X squared to the minus 1/2. And then you have a minus 1/2 in front, a 1/2 in front. And that's where you lose your 2. So your X was right, but it has to have the minus sign. Okay? Now, I have several students who do the chain rule this way. They do the inner function first and then the outer function. And it's fine. I'm just used to doing it the other way. Doing the outer function first and then do the inner. So if I were doing this, I would have said 1/2 of this to the minus 1/2, then times a minus 2X squared. You get there the same way, but yeah. So this is what you got. Okay. What are you going to do with that first derivative? You're going to square it. Okay. And that would be, squaring it loses the minus sign, so that would give you an X squared. Okay. I think I'm going to put this back in the denominator, and when you square this, you get R squared minus X squared, because it was over the square root, but you're squaring it, so it's just over the square of that. So this is your F prime squared. Okay. Got it? All right. Now what do we do with that? We're using the area formula that's at the bottom of the previous page, and I was talking about this before either one of you came in, so you can listen, go back and listen to that on Screencast-O-Matic. Your surface area is 2 pi, okay? The 2 pi is because, here's basically what we're doing here. It's what I said before. We're taking a little bit of the arc length here, okay? That little bit of arc length, and we're rotating that about the x-axis, okay? Well, the F value, this value is your Y value. That's the part that's being rotated, okay, around there. So that's the radius of rotation. So 2 pi times that radius of rotation, so that would be the integral from, well, we'll leave off that for a minute here, F of x, which is your R squared minus X squared to the 1/2 power, okay, times, now, what goes in here is your arc length that we were dealing with before. That arc length here, that's what you're rotating this 2 pi r around there, so it's this length here. What is that length? That length was your square root of 1 plus F prime squared, okay, and then your dx. Okay, so here is our F prime squared. What we need to do is add 1 to it. So let's add 1 to it. So that would be x squared plus R squared minus X squared over R squared minus X squared, right? Because 1 would be R squared minus X squared over R squared minus X squared. So you have the least common denominator, R squared minus X squared, and up here you have X squared minus that, okay? So hopefully you see that just turns out to be R squared over R squared minus X squared. Now we want to take the square root of that. Okay. Yes, sir. Are you through?
Yeah, you talking to yourself for real.
What's that?
I didn't see anybody when I came by the door.
Oh, okay.
All right. Good, man.
Did you finish?
Yeah.
Okay. All right.
All right. See you Monday.
All right. Have a good weekend. Okay. All right. So this part now becomes, I'm going to rewrite it slightly. The square root of r squared is just r over the square root of r squared minus x squared, right?
Why you can't write like r minus x?
Because that's not a perfect square. If that was r squared minus 2rx plus x squared, that would be a perfect square, but r squared minus x squared is not a perfect square. All right, now I want to, this is what this thing is, okay? So I'm going to put that in. So your s is equal to 2 pi times the integral. Now notice here, you have a square root of r squared minus x squared. Down here you have a square root of r squared minus x squared. So guess what? They go away. That's 1. This thing is in the numerator. That one's the same thing in the denominator. So it goes away. So basically you just have a dx. Okay? Now, I hadn't put in here what our limits are. Oh, yeah, I'm sorry, you have an r left, sorry. Sorry, I forgot the r. Yeah, the r dx. Okay? Now, I didn't put in the limits yet. And there was a reason for that. The way it's set up, this would be going from minus r to r. But if you'll notice here, everything here is the same as there, so the rotation would be the same. So why not just double it and go 0 to r? You okay with that? Okay. So we are going to double that, making it a 4 pi. Okay. Did you finish? Okay. Good deal. Thank you. Sorry about the interruptions. I got a bunch of people over there completing a test. Okay. So then this would be 4 pi 0 to r. Okay? But now, of course, your r is a constant here, so let's pull that on the outside too. Okay? So your surface area is equal to 4 pi r times the integral from 0 to r of dx. What's the antiderivative of dx? Antiderivative of dx? Antiderivative of the derivative of x? What gives you, when you take a derivative of it, do you get a 1? X. So this will be x. So this would be 4 pi r times x evaluated from 0 to r. Okay? What would that be? 4 pi r squared minus 4 pi r0, which is just that. And that is indeed the surface area of the sphere. I'm trying to recall if this book has those. Yeah, here we have. If you go to the front inside cover of your text, it's like 1 or 2 pages over. You see at the bottom it says geometry. Here you see a sphere. The area of the sphere is 4 pi r squared. Okay, we're dealing with capital R's, they were dealing with little r. You got it. Make sense? All right. Good deal. Let's move to, whoa, I see no example 5 here. So let's clear the screen here. Okay. What's that? Do you have an, what is your example 5, the bullet looking thing? Okay. In the new edition, example 5 is a different example, and I'll try to draw it here. My drawings are not too good. Find the surface area of the surface called a paraboloid that is obtained by rotating the graph of f of x is equal to the square root of x, okay, about the x-axis between 0 and 1. Okay. Now, let's first draw the graph. I will draw it hopefully on this one. Okay? 0, 0, 1, 1. Let's make this 1, so this would be 1. So there. And it basically is that. 4, 2 would be there, and 9, 3, so that's basically how it looks. We're revolving that around the x-axis, so you have this shape that looks like this. It's a paraboloid. It's a parabola this way revolved around there. That's called a paraboloid. You'll hit on that early in Cal 3. Okay, it's one of the first things we do in Cal 3. Okay. Did you finish? All right, good deal.
I went back and fixed some of the others.
I'm sorry?
I went back and fixed some of the others.
Okay, well, they're still going to be wrong because, yeah. But I'll grade the ones that you hadn't done. All right. It's good that you fixed them, though. Okay. So we want the surface area of that. So in this case, there's nothing you can do to help here. So your surface area is going to be your 2 pi, the integral from 0 to 1. That's where x is going. So you're going to be doing a dx out here. Your f of x is this. Now I should write that down. And this is your alpha of x, they call it in the book y, which is what it is equal to the square root of x. Okay? You have that here. So this is going to be, I'm just going to write it as x to the 1/2. Okay? That's the 2 pi r. That's the radius. That's the height that you have here. And that's what you're rotating around here. So that's where the 2 pi alpha of x comes. Okay? Now, the rest of this is your arc length. And your arc length was the square root of 1 plus f prime of x squared. And then you have your dx, right? So, one thing we've got to do here, I'll write that as x to the 1/2, okay, is take a derivative. What is f prime of x? Thank you. Did you finish? Okay. All right. What is your f prime of x? Okay. You're not integrating, you're differentiating. Okay. Yes. You do 1/2 x to the 1/2 minus 1, which is negative 1/2. Okay? Which is, I'm going to write it this way, 1 over 2x to the 1/2. Is that okay? What's the next thing we do? Take the derivative and then you square it. So f prime squared okay, are you through?
Yes, sir. I'm missing one. I didn't know it.
Okay. Sorry about all the interruptions. Okay. So when we square that, what do we get? 1 over 4 x. Very good. 1 over 4x. Now we add 1 to that because it's 1 plus that. So add 1 to it, and that would be 1 plus 4x over 4x. Right? That's what that thing is. Oh, we got to take a square root of it, though, don't we? So let's take a square root of it. And what does that give you? Well, it would be the square root of, I'm going to rewrite it slightly. I'm going to take out the 1/2, because 1 over 4, 1/4, if you took out 1 over 4, the square root of 1/4 is 1/2. So I'm pulling that on the outside. Okay? And what I've got left over in there is, trying to think if this is going to be helpful or not, x to the minus 1 plus 4. I don't know if that's helpful or not. I was just seeing if it would, because you have 1 over x, I'm sorry, yeah, plus 4x over x. So it would be, I don't know if that's helpful or not, but I'm going to do it now and see what happens. Okay. So let's rewrite our surface area. 2 pi times the integral from 0 to 1 of x to the 1/2 times, I'm not going to do it that way, okay? I don't like that, okay? Let me go back and change that. What I am going to do is this. I went too far with that one. I'm going to write this as 1/2 times the integral of 1 plus 4x over x, which I'm also going to write as 1/2 times the square root of 1 plus 4x over the square root of x. You okay with that? That is what I want. Because you see, this is the square root of x here, and that's over a square root of x, so those go away, and that just leaves me, I've got a 1/2, so I'm going to pull that out, and that wipes out the 2 there, okay? And then what we have is the square root of 1 plus 4x dx. Okay? Except I really don't like to write that either, so I'm going to go back and change again. Sorry about this. I'm going to take off the square root here and put it as a 1/2. Is that okay? When I'm integrating radicals, I don't like to integrate radicals, I like to integrate exponents. So I'm going to take this thing that we had here. 1/2 went out front, the square root of x, capital out that square root of x. You're left with that, but rather than writing it as a radical, I'm going to write it to 1/2 power. Okay? That integral, I think we can do. Can we? How? It's going to be a pi. I love the sound of that. 0 to 1. You want to do a substitution or just do it the way it is? Huh? Okay, what would that give you? Well, wait, if we're doing it the way it is, then let me erase this and we'll do the antiderivative. Okay, what's the antiderivative of 1 plus 4x to the 1/2? It's going to be a 1 plus 4x raised to the 3/2 power. Raising to the 3/2 means I got to put a 2/3 here, right? Then I got to do a chain rule, and that 4, you have to do the backwards from what derivatives are. With derivatives, we multiply by 4, now we divide by 4. So we're going to divide by 4. Okay? Well, 2 will go in the 4 twice. So if I'm not mistaken, this is going from 0 to 1. Yuck! Okay. So this will be pi 6, because that 6 is going to come out front. Okay? And basically that's going to be 1 plus 4 to the 3 halves power minus 1 to the 3 halves power. I know what that is. Okay? Because when you plug in 0 for x, you just get 1 to the 3. That's just minus 1. So basically what we got here is pi 6, yuck. No. Okay. Had to get rid of that. Huh? You're not finished? Okay, yeah, you put that on the top, that's fine. I'll grade what you've done so far. Okay. Not finished here, did you leave not finished on it? Right, here's the pencil. That means no F, right? No. All right. All right. I can't write down there because I'm running out of room and it's messing up. So let's take this out. Okay. Oops, that's not what I wanted. Okay. Okay. Let me take this up top here. That'll be a pi 6 times 5 to the 3 halves minus 1. Now, I don't think we're going to have get any good out of trying to take this cube root of that. I mean, the square root of 5 and then cube it, that'll be, I mean, you can plug that in your calculator if you want to, but you'll see they get the same answer, pi 6 times 5 to the 3 halves power minus 1. Same thing we got, and then they approximated it, which is plug into your calculator. And did you do it? What's that? Okay. According to the book, that comes out approximately 5.3304, which is a very good approximation. 5 decimal point, or 5 significant digits. That's pretty precise. Okay. All right. Now that was example 5, which is not in the old text. Let's move to example 6 in the new, which is example 5 in the old, and that's this one. Find the surface area. Okay. What's that?
I finished. Some of my answers, like right there.
Okay.
It's right there.
Okay, yeah.
I just ran out of room. Just some
Okay.
of them on the scratch paper.
Okay. All right,
Some
good
of them-
deal. Okay. Thanks. It doesn't matter. Close the other one, though, the one going to the other classroom. But don't close the outside door to the hallway, because that one is locked. All right, sorry about that. Here's example 6. Find the surface area S of the surface. Well, I'm going to blow it up for now. Boom, I blew it up. Okay. Find the surface area S of the surface obtained by rotating the graph of y is equal to x to the 1/2 minus 1/3 x to the 3 halves about the x-axis from 1 to 3. So there's the picture of it. Thank you very much for drawing it for me. I didn't want to have to draw that one. Okay, and you see it's okay to go 1 to 3. 3 is equal, alpha 3 is equal to 0. It's not negative, so you can go here. Basically, it looks almost like a bullet, or maybe if you're not into violence like that, a TP or something like that laid on its side or something. You get the general idea. Okay? There's what your figure is. And we want the surface area. I think we know the formula now, don't we? S is equal to 2 pi, the integral from 1 to 3. Now notice here, I don't know, I probably shouldn't say that. No, it's okay. I was going to say, I think you'll see in a minute why we can't go from 0 to 3, but we'll get there. What's the rest of it? Second? Yeah, you write that function, x to the 1/2 minus 1/3 x to the 3/2. That's your function. Times the square root of 1 plus f prime of x squared. Okay, and then your dx. So we got a little bit of work to do here. This, of course, is our f of x. And we've already written that in up there. And what do we got to do with it? Take a derivative, f prime of x. And what would that be? 1/2 x to the negative 1/2 second, yeah, minus 1/2. It's 3/2 times 1/3. That would be minus 1/2 x to the no, you're taking the derivative and not integrating. Decrease it by 1. No? 3/2 minus 1. 3/2 minus 2/2 is 1/2. Right. Okay. That's your f prime. Now what we got to do, and because it turns out this way, what I'm going to do here is write this as 1/2 times x to the minus 1/2 minus x to the positive 1/2. I don't know if that's going to be helpful, but next thing we're going to do is square that. Okay? So when you square that, your f prime of x squared is 1/4, right? Now, walk me through the rest of it. Okay, it's x to the okay, no. Okay. You're squaring that number, which is multiplying that exponent by 2. So that's x to the minus 1. X to the minus 1/2 times x to the minus 1/2 would be x to the minus 1. Okay? And then you have a cross term here, minus 2 x to the minus 1/2 times x to the 1/2. What's that? Okay. When you're squaring a binomial, you square the first one, twice the product, square the last one, right? Or you can FOIL it if you wanted to and see that. But what's the product of these two? X to the minus 1/2 times x to the 1/2. Multiplying two same bases, different exponents, keep the base, Add the exponents. Negative 1/2 plus 1/2 is?
It's 0.
0. Okay? So it's x to the 0, which is 1. So that's just minus 2. Okay? And then square the last term, and that's just plus x. Okay? You buy that? All right, now we're going to add 1 to that. Okay? Now, I'm going to multiply my 4 back through. I'm going to be 1 plus x to the minus 1 over 4 minus 1/2, right, plus x over 4. Okay? Now, only thing that gets better here, this becomes a positive 1/2. So you have x to the minus 1 over 4 plus 1/2 plus x over 4. All right? Well, let's get back in common denominator of 4, and that would be x to the minus 1 plus 2, isn't it? Okay? Right? Plus x. Okay? Now, that looks an awful lot like this, doesn't it? Except it's a plus 2 in there. And we got this by squaring that. So I suggest to you that this down here is x to the minus 1/2 plus x to the 1/2 squared. Because when you squared this, you got that. So when you square this, you get this. All you do is, yeah, right? Okay? Because the next thing we're going to do is take a square root of that thing, isn't it? This is the 1 plus that. So this will be the square root of x to the minus 1/2 plus x to the 1/2 squared over 2 squared. That's 4, right? So basically, lose the square root and the squares, and you've got that. Okay. So that is what thing is here. So this is s is equal to 2 pi times the integral from 1 to 3. Okay? Now notice what you got. Before you had x to the 1/2 minus 1/3 x to the 3/2 times, and what you have left here, you have a 1/2 that's in your denominator. So let's just take that 2 outside and lose that 2 there, okay? And just leave the numerator, which is x to the minus 1/2 plus x to the 1/2. And then you have a dx. All right. Well, this is multiplying two binomials. And it's not great, but we can do it. Okay? So now we have a pi, integral from 1 to 3. We're going to multiply these. Let's do this one first. First times first. X to the 1/2 times x to the minus 1/2. What's that going to be? Second? X to the 1/2 times x to the minus 1/2 is x to the 0, which is 1. Okay? Now you want to do the outer. X to the 1/2 times x to the 1/2 is x. X to the 1, right? Okay? Now do the inner. And that's going to be a minus 1/3. What? Negative 1/2, that would be x, isn't it? Add negative, or 3 halves to negative 1 half. 3 halves minus 1 half would be 2 halves. So that's going to be 1/3 x. Right? And then finally do your last. And the last is going to be another minus 1/3. Okay? And then that's going to be a, when you add the exponents, that'll be x squared. Want it? X to the 3 halves times x to the 1 half be x to the 3 halves plus 1 half is 4 halves, which is x squared. One over 3, there's my minus 1/3 x. This thing back here in the background is just bothering. See if I can get rid of it. I got rid of too much. Okay. And then we have our dx. Okay. Now we can simplify that a little bit, can't we? That's a pi times the integral from 1 to 3. Well, the 1's still there. But when you combine these two terms, that gives you plus 2/3 x, right? Yeah. Plus 2/3 x minus 1/3 x squared dx. Okay? Since I'm running out of room, I'm going to erase some stuff I hope I won't need again. I hope I won't need this, or that, or this. Now, I think I told y'all last time, these are not easy functions to find. That when you take a derivative, square it, add 1 to it, and then take a square root of it, it's something you can deal with. That's why this was such a weird function to begin with. They had to have something that would come out something you could do. Most of these are going to be, you can't integrate. This one you can. It's a mess to get there, but you can integrate it. How does that integrate? Antiderivative of 1 is x plus second 1/3 x squared. Very good. Minus, I'm sorry, 1/9 x cubed, and evaluate that from 1 to 3. Okay, this is going to be my pi. I like the sound of that. Okay, let's start plugging in the 3's first, and then we'll plug in the 1's, but we'll be subtracting the 1's. So this will be a 3 plus 1/3 of 9, which is another 3, right? Got it? Follow it? Minus 1/9 of 27, which is another 3, isn't it? Okay, guess what? Those two can go out. Okay, now we're going to subtract off our 1's. So that would be a minus 1, minus 1/3, that's from these two terms, plus 1/9, right? Okay, so that's going to be a pi times, and what do we have left? 3 minus 1 is 2, and 3/3 minus 3/3 minus 3/9 plus 1/9 would be a minus 2/9. So it'll be 1 minus 2/9, or 2 minus 2/9 would be 1 7/9. Okay, that's what all that turns out to be, which is the same as 16/9 pi, I think. I hope. Yes, it is. Look at that. See how you get that? Really, the hard part is doing the math, okay? The integration was not that bad. Now, going through all the steps to get there were long, but none of the steps were that hard. You had to have a little notice things. Oh, that is a perfect square that you make it go faster. But the hard part is getting all those fractions and stuff at the end. Okay. See how it works? All right, good deal. That finishes 8.1. Yeah. The summary is there. Then we have the preliminary questions. They worth doing or not? Want to do those? Up to you. Yay or nay? Okay. You don't care whether we do them or not? Okay. I would highly recommend doing them yourself then at home and checking the answers, because sometimes all five will be in the back, and sometimes just the odds, but those are usually in the back. So homework exercises, do either 1 or 3 or both. Any of the odds 5 through 9. Any of the odds 11 through 15. Any of the odds 17 through 33. Okay, I would definitely do maybe more than one of those, okay? Any of the odds 35 to 41. And it says you need a computer algebra system, but I don't know. You can set it up, see what you get, okay? Either 43 or 45. Then any of the odds, no, either 47 or 49 or both. That's up to you. Okay. There are some further insights and challenges. If you're interested in doing those, that's, completely up to you. Certainly don't require it. Okay. Sorry. My head's clogging up again. I don't know why. It's not cold in here. I think it may be all this sudden humidity. I'm not used to it. Okay. So let's get out of 8.1 and move to 8.2. All right, 10:30. My stomach's telling me it's lunchtime and it's lying to me. I mean, it's nowhere close. Okay. All right. All right. Same picture from the last edition and the new edition here. Well, not quite. Close, but not quite the same picture. Same type of thing. Again, I don't see any huge value in it, but I guess they're just trying to make it relevant or something. Since water pressure is proportional to depth, divers breathe compressed air to equalize their pressure and avoid lung injury. Okay? They have that same, it's a different picture, but same caption in both. We will be talking about the stuff that goes into that statement. Okay? And I guess to begin, let's start with this. Fluid force is the force on an object submerged in a fluid. Divers feel this kind of force, that's why the picture was there, as they descend below the water surface. Okay, and that's where that figure came from. Our calculation of fluid force is based on the laws that determine the pressure exerted by a fluid. And here are those rules. I think I'll probably write these down. Because I've got to get my pen back. Okay. fluid pressure is proportional to depth. So the fluid pressure, which we're going to call P, is proportional to the depth, which we're going to call H, because we're going to use it later that way. Fluid pressure is proportional to depth. Fluid pressure does not act in a specific direction. Rather, the fluid exerts a pressure on each side of an object. In the perpendicular direction. I was going to write that down, but it's such a the fluid pressure is exerted on an object in a perpendicular direction. I'll just put that. Fluid pressure exerted on an object in a perpendicular direction at every point. Okay. So if I was submerged underwater, let's just imagine that I'm lying horizontally, so I'm all at about the same depth, not a lot of difference there. So the pressure here is perpendicular here, it's perpendicular everywhere. Okay, that's what it's saying here. Now, so it's not just a constant, but it's perpendicular everywhere. The second fact, known as Pascal's principle, hint, hint, a possible paper topic. And by the way, let's think on papers for a moment here. I've received 1 from the 3 people in this class, so the other 2 need to get it. I've received first test from 2 out of the 3. I've received the second test from 2 out of the 3. So I'm talking to the guy I hope is listening, okay? Because y'all turn them in, please get those in. Now, you have your third test out, both of you, right, or not? Okay. Huh? What's that? Yeah, you have that. Okay. Y'all haven't turned that in, have you? Okay, good. Okay. So get those in. Okay. And by the way, next Wednesday is our last day of class for the term. So I'll be returning all of your tests to you then. So, talking to the other guy. I can't return your research paper to you because they periodically ask for samples of student writing, so I have to hang on to those. But your test I will be returning to you then. Okay? Now, all right. But what I was saying is Pascal's principle. Pascal, that's a potential paper topic. Who was he? What is his principle? How does it, how did he come up with it? What are applications of it? That kind of stuff. But anyway, all that done and said, here is the rule for fluid pressure. It combines both of those 2 statements we did before. And let's see. Here it is. The pressure at pressure P at a depth H in a fluid of mass density rho. Now don't get these confused. This is the English letter P, that's the Greek letter rho. This is mass density, okay? Rho. It's kilograms per cubic meter is usually what it's used. Could be in grams per cubic centimeter, but most of the time it's kilograms per cubic meter. G is the acceleration due to gravity, and H is the depth. Well, guess what, folks? Remember that first one? P is proportional to H. That was that first thing. Your proportionality constant is rho G. Rho is a constant for any given fluid, and G is a constant of nature here on the surface of the earth. So there's your proportionality constant. That makes that proportional equal to the equation here. Okay, yeah, the depth is, they're using depth being H. And I heard you say depth is height. Yeah, that's the H, standing for depth here. Height of below water. Okay, whatever you want to call it. The pressure acts at each point on an object in the direction perpendicular to the object's surface at that point. That was the second rule, Pascal's principle. Okay? So there is your fluid pressure. Okay. Fluid pressure. And by the way, pressure is given in, of course, when I go to write, it's going to shrink. Pressure is, anyone remember the units or the definition of pressure? Pressure is force per unit area. So that would be in newtons per meter squared. That's what pressure is, force per unit area. Okay, think of your tire pressure. I don't know if you're familiar with this, the little tire gauge. It's in PSI, pounds of force per square inch, force per unit area. Okay. Now, our first example does not require integration because pressure is constant. Okay? In this case, the total force acting on a surface area A is, here it is, if you have a constant force, okay, why they do that little bitty line here in the middle of a big white screen, even when I blow it up, it's still, okay. Remember I just said pressure was force per unit area, so force is pressure times the area, okay? And if you have a constant pressure, you're all at one depth, and that's why I had myself lying in a prone position in the water there. Multiply that by my surface area, and you get the total force acting on it, okay? So in other words, your force, F, is equal to your pressure times your area. Okay? That's a key. All right. That's when it's constant area. I mean constant pressure, not variable pressure. Okay? So I think that leads to example 1. I believe it's here. I'll blow it up for now, but as soon as I go to write, it's going to have to shrink back down. Okay. All right. Calculate, I can't breathe. Calculate the fluid force on the top and bottom of a box of dimensions 2 by 2 by 5. Okay? I think these are meters, aren't they? It's a pretty good sized box. Yeah, 2 by 2 by 5 meters. 2 meters this way, that's about my height. 2 meters that way, again my height. 5 meters that way, that's more like a 2-story building. Okay, so that's a pretty big box. Okay, about 6 feet by 6 feet by 30 feet. Okay, so more than 15 feet, sorry. Okay. And this block, or box, is, the top of it is 3 meters below the surface of the water. Okay? Now, all it asked for was the force on the top and the bottom. And it's fine, okay? Because that's all that really matters. Because if you were worrying about the force on this side, you have to have a variable thing. But guess what? It's exactly the same as the force on the other side. And the force on this side would be exactly the same as the force on that side, even though they'd be difficult to calculate, but they're exactly the same. So you're really only worried about the difference of the force between the top and the bottom. Okay? There's a constant pressure on top acting downward, constant pressure on the bottom acting upward, because they're always perpendicular. These are not constant forces here, but they're identical forces here and here, so they are going to cancel each other out. So we're only really interested in top and bottom. So what would be the force on the top of this? What's the definition of force? Pressure times unit area. Now the pressure was what from our earlier thing? Rho GH, right? Rho GH. Rho is the density of the water, and I think they said this is in water, but it really doesn't matter. Let's see. Yeah, density of water is 10 to the third, or 1,000 kilograms per cubic meter. So that's the pressure at the top. No, that was density of water. And density was rho. Oops. Okay, I'm going to have to shrink now. Okay. The picture anyway. So pressure is rho GH. And we're going to do pressure at the top, and we'll later do it at the bottom. So height of the top. Yes, ma'am. Did you finish? Did you disrupt the class too badly? Okay. All right. Okay. Are you done?
Yeah.
Okay. So erase the not. Okay. Okay. Sorry about the interruptions. Okay. And then we're, got the wrong pen. Force is equal to, what did you just tell me? Pressure times area. Okay? The rho they just gave us, rho for water, is 10 to the third kilogram per cubic meter. We know what G is, or I hope you do. What is G? 9.8 meters per second squared. And the height, we know what that is. Depth, that is 3 at the top. So your pressure at the top is going to be 9.8 times 3. Someone punch that in on a calculator somewhere and tell me what that is. 9.8 times 3. It's 29.4. Okay. Okay, yeah. I was going to use 10 to the minus 3, but 29,400. And that would be, pressure is Newton per meter squared. Okay, it's force per unit area. SI unit would be this. Let's see if that's indeed right. A Newton is a kilogram meter per second squared, right? Sorry. I times another meter, okay? So that would be kilogram. Okay. And then our HT was 3 meters, okay? So when you multiply those three together, you get kilogram meter per second squared. That's going to be your Newton. And then this meter wipes out 2 of those meters, and that's meters per Newton per, okay? So this is 29,400 Newton per meter squared. And what's the area of the top? 4 square meters. Well, the square meters disappear, and that leaves you with, oh boy, 70, someone punch this in, 6, second, 117,600, okay, my numbers are way off, so we're going to get them closer, 117,600. Newtons. Okay? That's the force at the top. Okay. Yeah. Okay? Now, at the bottom, what's the pressure at the bottom? Well, the rho G are the same. That would be 9.8 times 10 to the third. Okay? I won't worry with the units now. They'll work out the same. That's multiplied by the height, or the depth, and the depth at the bottom is how much? 8. Okay? Meters. I said I wasn't going to worry about them. But anyway, that comes up to be 9.8 times 8.
Um,
70, yeah.
that means it'll be 313,000.
Okay, say that a little. Second. 300.
313,600.
Oh, 600. Is that your final answer? Oh, okay. Okay. I was going to say that's not this. Okay. This would be the force. That would be newtons. Is that what you're saying? Or is that the pressure? Oh, it's pressure. Okay.
No. Yeah,
Huh? It's the force. It looks like the force to me, because 8 times 9. This would be something a little bit less than 80,000, wouldn't it? Yeah. And then multiplied by the 4 again, that would give you that. Yeah. So I'll buy that. Okay. Yeah. Now, in the next example, which looks a lot like it, in fact, it looks exactly like the same box, but what we're going to be doing here, it's saying calculate the fluid force on the side of the box in example 1. Okay, well, all 4 sides are the same. So we're looking for the pressure on one side. Well, that's not a constant depth, so the pressure is not constant. The pressure is constant on a very small increment of depth, because this plate here and this plate here, this plate of water, you might say, that's at pretty close to a constant depth. Okay? The trouble is, it's different from here, different from there. This is in between those two. So you're going to have to calculate your pressure in an incremental fashion, which basically is saying do your force in an incremental fashion. So each strip has an area of the length of 2 and the width of delta y. Okay? So each strip has an area of 2 delta y. Okay? Now let's just look at these. You start at the top here, your depth is 3, and then your next step here would be 3 plus delta y, one of your increments there. Every one of them is that, 3 plus j minus 1 delta y. That would be each of, this is 3 plus delta y, 3 plus 2 delta y, 3 plus 3 delta y, 3 plus 4, 3 plus j delta y. Okay? And then at the bottom, your y sub n is 3 plus n delta y. But delta y is 5 divided by n, because you've taken that 5 and divided it in equal pieces. So that gives you 8 at the bottom. Okay? So each of the strips has an area of 2 delta y for this box here. Okay. So what we're going to do is integrate that. Okay? Sorry. Let me get out of that. I'm so sorry. I can't talk. Okay. So let's go back and do like we did before. Let's first calculate the pressure. Now, what is the pressure? It's the rho. That hasn't changed. G, that hasn't changed. But, second? Yeah, and it would have been H, but now it's going to be delta Y. This is the pressure on each little strip. Okay? No, that's not right. it's our y, I'm sorry, I didn't want to put delta y, I want to put y sub j. Why put delta y? Okay, y sub j. But you see your y sub j is 3 plus j delta y. Okay, so that's what's going to go in here. 3 plus j delta y. Okay, but don't sweat that too much yet. Okay, that's the pressure at any level there. Okay, now the area we just said was going to be, here it is, each strip has an area 2 times delta y. So your force is equal to pressure times area. So this would be rho g, yeah, okay, we'll put y sub j times your area is 2 delta y. Okay. That then is what we're going to be integrating. Okay? So this is incremental force here. So the total force would be the integral 2 rho g times the integral of y dy. Okay? That's what ultimately it comes down to. Okay? Now they kept the 2 on the inside. You don't need to. Okay? Now, the reason they kept it on the inside, the 2 was just for our particular problem here. Okay? They're not going to calculate anything here, but that's how you would do it. Okay? Now, what if you had a different issue? You don't have a rectangular slab that you're doing. You have a dam or something like this, which is, let's just imagine that this was this would be a very good dam because you got water over the top of it. But let's say it's a container that you have submerged underwater. What would be the pressure of that end of it? And this is a parabolic shape here. Okay? What you have to do is come up with a length here, and that length is going to be some function of your depth. If y is equal to 0, you're at a certain depth, A. And then when you're at y equal, when you're the nth surface down, then you're at another f of y. Your y is your depth, and your f of y is how, whatever that measurement is. If that's a parabola, then you have to figure that from the area, from the formula for the parabola. You have to come up with that. But still, the area of the shaded strip here would be your f of x times f of y times your dy. Okay, that's always going to be the area. Before the f of y was 2. Okay, it was a constant 2. This time it's a variable. It changes as you go down. Okay. But still, your force would then be rho g, the density of water times the acceleration due to gravity, the integral from A to B. Now these are along y, so it's dy. A is the top part, B is the bottom part. Okay, that's why that's done that way. And then you have your y, f of y, dy. Okay, now, from before, remember it was y sub I, so that's where the y came from, and then this function of that y at that value. Okay, that defines the curve here. So your depth is your y times your length times your thickness. That's your dy. And that gives you your, and you multiply that by rho times g. Okay. A lot of blah, blah, blah without any examples yet, but we're getting close. Here is your theorem 1. Okay. Another part of my problem today is, with all the weather last night, it didn't bother me so much, but it bothered my wife a lot. So she was up and down checking things and stuff. So when she doesn't sleep well, I don't sleep well either. So that's part of the day. I'm really feeling almost lightheaded. But it's just tiredness, I think. Here's theorem 1. The fluid force on a flat surface submerged vertically. Okay? Fluid force F on that flat surface of an object submerged vertically. But you have increments in y, so there's your dy. Your f of y is the length. This is your length of whatever that surface is. That's some function of your depth. Okay? Then the y, how deep it is between A and B. Okay? So your rho g, that was from your density, your pressure, rho gh. Basically, your h is the y there, and then your area is f of y times dy. So you can think of it that way. If you think about what we said before, the density was rho g y, right? Except we were calling it h then. The rho g is on the outside, so it's there. So there's your y, which was your h up here. Then times the area, force is pressure times area. So the area is the length times the thickness. So there's your f of y dy. Okay? So that's what it is. Where f of y is the horizontal width of the slide at any depth y, and the object extends from a depth y is equal to a to y is equal to b. So this is the upper part to the lower part. So it's exactly like what we had before, but now in terms of an integral. But it's rho g, this is like your h, the width of that is your function of h, your function of y, and then the thickness of it is dy. Okay. I think we're now ready for example 3. And I think this is it. Let me blow it up for you to start with. And let's see if we can figure it out and if everything makes sense. Calculate the fluid force on one side of an equilateral triangular plate of side 2 meters submerged vertically in a tank of oil of mass density rho is equal to 900 kilograms per cubic meter, shown in this figure. Okay. How are we doing on time? I know sometimes he has to go early, but it's 11, so we got 10 minutes. Okay. Now, according to this figure, it appears to be the vertex of this equilateral triangle is at the surface. So there, your y is going to be 0. Okay? And you're going down to some depth here. Well, this is an equilateral triangle of each side is of length 2. Okay? So, one thing you got to figure out is how far down you're going. Okay? Now, I don't know if this is helpful to you or not. Hopefully it is. Let's take that equilateral triangle. Okay? And let's bisect it here. This is just for construction purposes. It's not anything to do with the problem, really. Now, if it's equilateral triangle, that means it's also an equal angular triangle, so that each angle is 60 degrees, right? Or pi thirds if you prefer to think in terms of that. These up here are then 30 degrees because you've bisected them, and they have to add to 60, so 30 and 30, 60. Okay? We know this side here, this lateral side is 2, just like the base was. This is 2, and half of this is, of course, 1 and 1. Right? What we're interested in is what is the height, the depth of the bottom of that. Okay? Well, this is a 30, 60, 90 triangle. The short side is always half the hypotenuse, and the other side is, sure enough, the square root of 3. So they were right in labeling that square root of 3. Remember that? Okay. So that's where they got the square root of 3. Okay. Now, so what that gives us is our limits from 0 to square root of 3 of the integral we're going to wind up with in a minute. In fact, let's go and get it down. It says calculate the fluid force F is equal to rho g times the integral from 0 to root 3. That's all we've done so far. Okay? We can go on and put the y in because y is going to be part of that. That's the depth. Okay? So that's going to be there. The f of x, f of y, we've got to figure out how long this is at any depth. Well, we know that if that 0 is 0. Okay? That's pretty clear because the length up here is 0. Down here it's 2. So it's varying from 0 to 2 regularly over that depth of root 3. Okay? So what does that tell us? Okay? Well, I see a ratio here. I see the ratio of, and the ratio is going to be, let's call it H to F, where F is that thing there, is going to be root 3 to 2. Okay? The ratio of the depth here, in fact, let's make that y, because that is y. The depth is y. Okay? So the ratio of y to F where F is the length there, is the ratio of 3, square root of 3 to 2. Let's make sure that's right. Makes sense. When y is 0, your width is 0. Wait, we better not have the y at 0. Okay. When y is 2, no, I have it backwards. Wrong.
Yeah.
No, when y is root 3, this F is 2, and when y is, I guess the better way to express this, goodness gracious. Let's write it this way. Root 3 F is equal to 2y. So F is equal to 2 over root 3 y. Now let's plug in and see if what we get is right. When the depth here is 0, your width is 0. Yes, that works. When the depth here is root 3, that's as far as it's going to go. Y is going to root 3, then that F is 2. So yeah, this is right. Got it? Okay.
So that the integral like 0 to root 3 means 0 from here to
Yeah, you're going from
higher though, right?
0. You're doing increments of dy's. So the y is going from 0 to root 3. Yeah. So that's that up there. The y, and this is your f of y.
Oh, that's the right. That fx is the.
F of y is your width at any place down. Okay. They drew just a red line. Let's just imagine this is a bar right here. The depth of that bar is y. What we need to know is the length of the bar. That's the Fy. The thickness of the bar is your dy. Right? So basically what you have here, the force on it is the pressure, which is rho Gy, right? Times the area of that, and the area of that is going to be whatever that f of y is times dy. So rho g y, f of y, dy. That was our formula, right? But the f of y is 2 over root 3 y. So this will be rho g, and let's go on and put the 2 over root 3 out here. And then that'll be the integral from 0 to root 3. And that's going to be the y from here times the y there. That'll be y squared dy.
Show me that the integral, the 2 point in the picture, to me like which part, like integral one.
Okay.
0 to
Okay. Okay. I'm not sure what you're asking.
I'm asking like integral like 0 to root 3.
Okay.
Show
Okay.
me that 2 point.
All right. All right. What we're doing here is the pressure. Start with the pressure. Pressure is rho g y. We used to call it h, now we're calling it y. So that's the depth. Rho g y. So for this strip right here, its pressure is rho g times that y. Okay? That's the pressure. Force is pressure times the area.
Yeah.
The area is going to be the length of this times the width of that. The width is your dy, the length is your f of y. Okay? And what we did over here was set up the ratio between y and f of y. We know that's got to be root 3 to 2. So y times the f of y, that ratio there has to be the same as root 3 to 2.
Oh, even though it's in smaller. I mean, it looks to me like, I don't know. Okay.
Yeah. So by doing that, y is the f of y as root 3 is to 2. Because it varies regularly from 0 to 2. So it's going to be coming down just that way. And then setting up to get that length as a function of y is then solve for the function, and that would be 2 over root 3y. So that's what goes in there. So that's 2 over root 3y there. Here's the y part. Y times y is y squared. Here's 2 over root 3 here. There's the rho g there. So I think we got everything accounted for. Now the calculus is the easy part. I mean, setting it up is the hard part. It's the complicated part. This would be 2, and by the way, rho was 900 kilograms per meter squared. I don't know if I should keep these units or not. Meter cubed is. Better be, yeah, meter cubed. Times 9.8 meters per second squared. Divided by root 3. And then you tell me what the antiderivative of y squared is. Over 3, exactly. And this is going from 0 to root 3. All right? Now, rather than carrying all that around, it'd be a good idea just to calculate that. I won't write it down again. But this is going to be y cubed when y is equal to root 3. That would be 3 root 3 over 3. Okay, and minus the 0 part. So this is just the integral part is just going to be root 3. Okay? Well, that root 3 are going to cancel that root 3 out. Okay? So what we have left is 2 times 900 times 9.8. Well, let's see. How would be the easy way to do this? It's not really an easy way. 900, yes, sir. You need a key? Okay. Is it 11:10 already? 11:12. Okay, we'll finish this problem. We'll be through. So 900 times 9.8, that's going to be some big number. More than, just under 9,000. 8,000 something another, times 2. So that's going to be 1,700, just under 1,800. Let's see what they got. 1,000 I meant. That's 17,640. Okay. I didn't do all the math there, but
17,640.
got it. Okay. So that comes up approximately 17,640, and that would be newtons. All right, we got down to example 3. Next time we'll do example 4, bottom of the page there, and we almost finished 8.2. Homework exercises here, you can do any of the odds. Yo. I'm just guessing. Let's do any of the odds 1 through 19. Okay? Because we're almost through, so that almost gets us there. Okay. No, let's maybe not do 19. 1 through 17. I think that'll be okay. All right, good deal. Okay.